Thank you so much for coming, despite the weather. I know it's pretty exciting right now. Hopefully my slides will be up here in a minute. I'm really excited to be here today. It's my first trip to Moscow. I've been having a great time so far. I'm going to talk to you today about machine intelligence, machine learning, and how we use it at Google, and how I think these technologies are evolving, and how they affect the kinds of things that we build today. In order to do this, I'm going to take you through, we have a technical difficulty. It's amazing that no matter how long you work on artificial intelligence, the simple things never seem to work out. Okay, so I'm going to talk to you today about machine intelligence and how I think it's changing things in the world today. One of the things that you may have heard recently is that just in the last few days, the DeepMind AlphaGo player defeated the Chinese world champion at the game of Go. And this was a follow-on to the games that were played in Korea against the champion there. And actually, this is something that was not predicted to happen for more than 10 years from now, that machines might be able to best the best human players at this game. And so over the course of this talk, I'll kind of explain to you how it is that we're able to make these kinds of things possible ahead of schedule. But one thing that is very important to understand is that machine learning is already in all of our hands today. It's already in products and services that we all use on our smartphones, whether it's in maps or email services or how we use photographs. There are two kind of big ways that machine learning is affecting the technologies that we're all using. So one thing that it's doing is it's taking existing products and services, things that we're all familiar with, and making them better. So things like Google search or machine translation, those are things that we've had for some time, but they're getting better using machine learning. But there's also something else happening, which is that machines are starting to enable us to do things that were previously impossible. So a couple of years ago, we launched something called Smart Reply that is able to write automatic email responses in English, and that's something that would have been considered science fiction even a few years ago. Over the course of this talk, I'm going to explain to you sort of what I think of as the four basic elements of making machine learning systems work in practice. And my hope is that by explaining to you what these elements are, you'll be able to see where the applications might be in the future. But I think that it's up to all of us to choose what those opportunities are. To get started, I just want to establish some terminology because I know we come from diverse backgrounds. So one of the important academic disciplines here is artificial intelligence. What is artificial intelligence? Artificial intelligence is the science and the art of trying to make machines that at least have the appearance of being intelligent. It's not really to make machines that are like people, it's just to make machines that have the appearance of intelligence. There's a newer and smaller discipline called machine learning that is really about making machines that learn, machines that take experiences or data and change their behavior. And it's really at the intersection between these two fields that we see a lot of the activity today. And part of the reason why this is so important is that while traditional AI systems were programmed to be clever, as if there were some recipe for intelligence, machine learning-based systems actually have to learn to be intelligent. And it turns out that that is easier. It's easier for us to build machines that learn than it is to give instructions for what intelligence is. And so there are some concrete historical examples that I've put up here. So IBM Deep Blue was the chess computer that famously beat Garry Kasparov at the game of chess. That system was a classical artificial intelligence system. It was a chess engine that was beautifully engineered to play this game of chess, and specifically to play against Garry Kasparov. AlphaGo, the Go system, is very, very different. This is a system that is not pre-programmed with the rules of Go, but instead has to learn to play the game. And it was not possible for us to build a system, to engineer a system to be good at the game of Go, but it was possible for us to build a system that learned to play the game of Go. A third discipline that I want to mention here, because in science fiction it's often confused, is the field of robotics. So robotics is really about building machines that move autonomously. And while there is some interaction between robotics and machine learning, which I hope to show you near the end of the talk, mostly these are separate disciplines. In the land of science fiction, of course, we always think about these three things all together. Machines that appear to be intelligent and learn and move on their own. But right now, this is actually really a very rarefied space. So just to really make this very specific, the classical artificial intelligence approach was based on rules, very specific instructions. So, for example, the Google Gmail spam detector used to work with on a system of rules that looked for critical features of an email that might be a clue that something was spam. Whereas the new machine learning-based system, it's still a piece of software, but it's a different kind of software. It's a piece of software that tries to classify emails as spam or regular emails, and then when it makes mistakes, it makes changes to itself so that it's very slightly better. And it's this part, change yourself to make fewer mistakes, that sounds magical. And I'm going to spend the next few minutes removing all of the magic from that. Because it's very important to understand that there's no magic here and that this is actually very, very simple. So the way that machines actually learn is that an engineer builds some specific system that has predefined inputs, things that the machine takes in, and predefined outputs, things that the machine puts out. And our goal is to build something that does this input-output relationship very well. To make a very simple example here, let's imagine that what we want to do is we want to build a system that predicts the average test grade for a student based on how many hours they've studied. This is a very simple problem, and we want to build a machine that learns to make this prediction. So there's some relationship between studying and score, and this is what the machine has to discover by learning. So how does the machine even know what the relationship is? It could be anything. Maybe it's a very easy test. Maybe it's a very bad test where no matter how long you study, your score doesn't go up very much. But these machines, they know nothing about the world. They don't have any prior experience that they leverage. So they might think that this is equally likely, that the more you study, the worse you do, or even crazy hypotheses like this. So it's only through their learning, through their experience, that they have to learn what the relationship is. So how does a machine even know what line it's drawing, what hypothesis it's entertaining? And the answer is that there's always some underlying mathematical equations. So in this case, the equation for a line is a very simple relationship, and we all at least use these letters in the US. Y equals WX plus B. The height of the line is proportional to the slope plus some offset. And if the machine wants to draw a different line, it just changes those values of W and B to change where the line starts and how quickly it grows. So this is the second main component of a machine learning system, is this idea that the model, the machine, is a set of equations. It's a piece of software that implements some equations, and then there are these parameters, the part of the system that actually specifies what the machine does, what the machine has learned. And the way that we find these parameters, that's really the process of machine learning. We start out not knowing what these parameters are, and that's what the machine learns. So how do the machines do that? And the simple idea is that they learn by trying to reduce the size of a mistake. So let's say we turn on the machine, it knows nothing. It sees how one student studies. They study for 2 hours and 15 minutes and they get an 82 on the exam. What the machine takes away from that is all that it does is it sees the error that it has made and it makes the error smaller. It doesn't correct the error. It just makes the error smaller. So it moves the line up to make the error smaller. Then it sees another student who studied. It sees the error that it makes the error smaller. That pulls on the line. And it just keeps doing this in a very dumb, repetitive way until eventually it gets the central tendency of these statistics here. Now, for anyone who's an actual statistician or data scientist, this is a terrible way to learn to fit a line to some data, but the powerful thing about this approach is that it applies to even very complicated machine learning systems, to even very complicated equations, and we'll see that next. So, as simple as it is, as simple as it seems, this really is how these complicated software systems are designed and implemented, and it's even how the academics organize themselves at conferences. There are sets of academics who focus on the modeling part, on what the right set of equations is to use for some process. There are scientists who focus on the learner part, the part that compares what the model predicted to what the truth actually was and knows how to change the parameters. And there are some who specialize in the representation of the parameters themselves. And then once we fit this model, prediction is very easy. We just put in an input and we can make any output. So now my guess is that if someone studies for 3.5 hours, they'll get a 91 on the test. So this basic framework repeats itself, and it really actually is how Google learns to detect spam, is that we have a model, we put an email in. Now instead of the hours studied, it's a whole email is the input. And the output is just, should we put the spam label on it or not? But it has this same structure, and we learn from whether or not the user marked it as spam. And we have to do this many, many times because we learn very, very slowly, just like we did in fitting the line. But this is also how Google learned to recognize objects in photographs. This diagram still applies to how you know that there's a cat in a photograph. And that's the amazing thing, that this simple diagram applies to all of these settings. So machine learning isn't magic. It's just this simple engineering approach that if you have a problem where there's a crisp input-output relationship and you have examples, maybe a machine can learn to do it on its own. Maybe you don't have to write a specific set of instructions for how you go from the first step to the last step. But so why is this happening now? Why are we talking about machine learning in this decade instead of the previous decade? And the answer to this question actually kind of is surprising in that even though this is very general, it's very slow. And it's so slow that often it requires millions of times going around. And the fact that we were waiting for this to work actually reminds me of the human quest for powered flight. So even in the 1890s, people had good designs for flying machines, but they never got off the ground. And the reason that they didn't get off the ground was because internal combustion engines were very heavy and they were not very powerful. They were made of iron. And the first people to fly were people who made their engines to be as light and as powerful as possible. But if you fast forward 10 years into the future, all of a sudden it's easy for people all over the world to take their designs and be able to fly. And the same thing has happened in machine learning, but the engine we were waiting for was computational power. So, I didn't do it. I'm going to unplug it and plug it back in. The machines are ready to learn again. Okay, so what we were waiting for was we were waiting for machines to become fast enough that they could make these many millions of cycles in a reasonable amount of time. And this has happened through the natural increase in speed in CPUs and central processing units, also in the realization that we could build, we could use graphics cards in order to make this process cheap and effective. And even more recently, people have started building custom hardware. So for example, Google has a processor called a tensor processor that is specifically designed just to make machine learning fast and efficient. There's nothing special or magical about any of these pieces of hardware. It's only, oh no. Oh yes, so we need that computational engine in order to be able to go round and round many times, and we also need examples to learn from. We need inputs, and we need examples of the correct output. What is the output that we're looking for? And so with these two facts in mind, I can actually now introduce sort of the first two ingredients that we always look for. So one ingredient is these examples to learn from. And if you have a setting where we don't have many historical examples, it's very difficult. I live in California. I would love to be able to predict earthquakes, but there are just not that many earthquakes. So it's, which I'm very happy about. But it makes it very hard to learn to predict earthquakes. But there are millions or hundreds of millions of pictures of cats on the internet, so it's very easy to learn to recognize cats, because we have plenty of cats. The second thing that's really essential is computational resources, having the ability to be able to make the machine go around many, many times to make these small changes. And these two things were what we didn't have in the decades past, but now we have today. In order to explain to you the next two ingredients, I have to go a little bit deeper into how some of the components of machine learning systems work. So one of the technologies that I want to explain to you is a specific kind of machine learning that's called deep learning. And this is an example of a trend for the searches on Google for machine learning over time as it's become more and more popular. And that's because of this deep learning phenomenon. So what is deep learning? Deep learning is actually the technology that allows us to, for example, recognize cats as opposed to just predict test grades. So it's really actually only a change to one part of this picture. It's a change to the set of equations that we use in the model part. So it's only a change there. The other parts of the system have not changed, but what we've done is we've said that the kind of equations that we are going to use are something called a deep neural network. You don't need to understand very much about the system of how these systems work, other than one simple concept, which is that the idea of deep learning is to break something up into many small steps instead of trying to make it in a few giant leaps. So when I was a grad student, when you went to a machine learning conference, people were trying to get from the input to the output in 2 mathematical steps, or if they were really bold, 3. And somehow, I don't understand why we thought this, but we thought that you could go from a picture of a cat to the word cat in 3 mathematical operations. And it turns out it's very hard, maybe not possible. But what is possible is to get from a photo of a cat to the word cat in 20, 30, 50 small steps. And the basic insight of deep learning is to make many smaller steps. It's actually also not something that's a terribly new idea. So the basic underpinnings of deep learning are based on something called artificial neural networks, the fundamental mathematics of which were worked out in the 1980s and 1990s. So the mathematics that I use every day is actually something that I was taught in school and told doesn't work. But the thing that's interesting about it is that the idea is that we make simple trainable parts that then have to work together in order to solve a problem. Now, my PhD was actually not in computer science, it was in neuroscience, which was me spending a long time learning how little we know about the brain. But deep neural networks are based on some of the little bit that we know about the brain, but not very much. So the commonalities between real brains and artificial neural networks are very thin. So it's in the human brain, all computation is done by individual cells called neurons. And these neurons are not particularly clever as individuals, but they have to learn to work together in order to solve complicated tasks. This is also true in artificial neural networks, but instead of individual cells that are making decisions, we have individual mathematical functions. And to engineers, these are the simplest kinds of individual mathematical functions you can have. None of them are very clever, but what we do is we put together 1 million or 1 billion of them, and we have them learn to cooperate, learn to work together to solve some task. And that's actually how these things that were science fiction a few years ago basically work, which is that if we want to recognize an object in a photograph, we put a photograph into the bottom of the machine learning system, which is just a set of equations, and there are a bunch of equations, individual decision makers at the bottom, that try to make decisions that are useful to ultimately guessing whether a photograph is of a cat or a dog. And when you initially start this system, none of the elements know what it is that they're supposed to do. But what happens is that over time, the system is able to learn each individual decision maker is able to learn to play a part that helps the whole solve the problem. Another thing that's really important to understand about deep learning is that it's not one mathematical function, it's not one approach. It's actually a bunch of little pieces that you assemble in different ways in order to solve different problems. So the real diagram for being able to recognize cats in photographs that Google uses is this one here, which is obviously a little more complicated than that simple 3-level system. But these kinds of architectures, these are 2 Google researchers who have published various models in this space, but people are always coming up with new architectures, new ways of putting together these building blocks. It still learns from example, it's still that same simple idea that we saw about learning to predict test scores, where now we're going to learn from stacks of photos. So I'm going to have a stack of photos of cats, a stack of photos of dogs, and initially the machine is going to make wrong guesses about whether it's a cat or a dog, but it's going to make its errors smaller and smaller and smaller over time. And when the machines are done, they're actually quite good. So they're able to do precise classification of various objects in the world, whether they're flowers or dogs. And this is much better than the kind of thing that I would do. I would think that they were all Siberian Huskies, but no, there's this other Alaskan dog, looks the same to me. But one of the things that's impressive is that these systems have good generalization behavior. So it recognizes these 2 photographs as pictures of a meal, even though they have very little in common. And when they make mistakes, the mistakes are sort of understandable. So it thinks that this slug is a snake because it's some animal with no legs, and it thinks that maybe these donkeys are dogs. But this isn't just a science experiment, we actually make real products out of this. So Google Photos, for example, is a system where now you can search your own photographs for any concept that you care about. So for example, I can search my photographs for my photos of Siamese cats. I only have 2, so it returns the first 2 photos as Siamese cats correctly, and then it starts filling in with other cats because it recognizes that cats are similar to each other. But this comes back to the point that this is not just one function, but it's a set of building blocks. And if you put the building blocks together in different ways, you can build different things. So deep learning is also, it's how we recognize photographs, objects in photographs. It's also how we recognize speech. So if you use speech recognition from any company, whether it's Microsoft or Google or Apple, we're all using deep learning by example to do this. Modern machine translation systems go from text to text, and there are even some new exciting applications where, for example, we're able to take an image from a microscope and be able to guess various parts of the cell just from this very vague, grainy photo. And this is something that the machine can learn to do by seeing examples of what the right answer is. So this kind of brings me to what the third ingredient is. And this is really the most important one today, and the thing that is the rate-limiting step on progress in machine learning, and that's human creativity and ingenuity. Machine learning is fundamentally a craft. It's not an exact science. It's like learning to blow glass. And the engineers and data scientists who learn to do this have to have some taste and some practice in this art in order to get good at solving problems using this technique. It's not as though you can just hire a machine learning expert and you always get the same answer. And just to give you some examples of I think, the surprising creativity that's involved is, a few scientists discovered, quite to our surprise, that they could take a deep learning system and feed it back on itself that caused it to have visual hallucinations. And this is something called deep dream, and there are now whole sets of artistic explorations in how we can make machines hallucinate interesting things, completely unexpected use. AlphaGo, the system that plays the game of Go, the way that creativity was used there was that what the inventors did was they used deep learning, again, to learn to study the games of masters, to try to predict what the next move would be of the game, if a master were playing this game. That was the first thing that they did. And then they added another layer of creativity, which was then they switched to a different kind of machine learning using the same kind of architecture, and then had the system play against itself. And it took a lot of creativity to see how to put these pieces together, even though the basic building blocks are still the same ones that are used in speech recognition and all of these other technologies. Another example that was really surprising to me is this smart reply technology of writing emails for you. So in 2009, Google actually put this out as a joke on their website, that the next version of Gmail would respond to emails for you. Because in 2009, that was obviously impossible. But 6 years later, it was launched as a real product. And 6 months after it was launched, 10% of all mobile replies were being generated by people just tapping on one of these automatically generated responses. And to me, that's really remarkable. I don't think that this number will go up, because the point of this system is 10% of the email you get only ever deserves a one-sentence reply, and there's not a lot of creativity. And by looking at many examples of that, this system is able to learn to reproduce it. Machine translation is another area of great progress recently, where we've learned by examples. So we've learned now by taking an entire sentence in English and an entire sentence in Russian, and we just give them as pairs. And we ask the machine, we say, okay, given the English sentence, just predict the first few letters of the first word in Russian. Okay. Given the first few letters of the first word, predict the next few letters of the first word. And so on and so on and so on. And just by studying these examples, we were actually able to build a machine learning system. Again, it's all the same. It's still machine learning, it's still learning by example, it's still a deep neural network, but it's a different set of pieces. And now all of a sudden you build machine learning systems that start to be much better at machine translation. I don't know if you've tried English and Russian recently, but hopefully in the last year it's gotten much better. Tell me if not. And because these pieces all fit together, it's surprising how flexible and creative you can be. So it was a very small number of engineers, I think 3, who were able to take one machine learning system that recognized text in images and weld it to another machine learning system that did translation, hack up some graphics, and now you have an augmented reality product called WordLens, where you can just hold things up. And I swear to you, I ordered at a restaurant yesterday over by Red Square. I had a Russian menu, and I ordered successfully by holding my phone up to the menu. It's not perfect. Many words it didn't get, but it was enough that I got what I was hoping for. It was very tasty. And another funny creative opportunity is that, so as I said, I was a neuroscientist, and one of the things that we're always trying to do is understand how the brain is constructed, how real neurons are connected to each other. But one of the problems is that there are so many neurons in the brain that it's very hard to measure. Now we're using artificial neural networks to try to better understand real biological brains. And the way that we do that is by taking a brain, slicing it up, putting it under an electron microscope, and then using machine learning algorithms to try to trace the connections that neurons actually make. And these pictures are very complicated and very hard to interpret. It takes professional biologists a huge amount of time to interpret a single image, but what you're able to do is you're able to give it take a machine learning system and have it learn to fill in these neurons by learning from examples that the biologist gives to the system. And the way that this works is actually by growing. What it learns to do is it learns how to extend a neuron in space through the data without making a mistake. And this is the process by which we're able to do this. This is still an emerging technology, but it's very exciting to see these technologies improving even biological sciences. Another example is I mentioned at the beginning of the talk, this interaction between robotics and machine learning. So remember, at the beginning we said classical AI, we have rules, right? And classical robotics has rules for motion control, how the robots move. What if we apply machine learning to that and have the robots learn to move? So this is a video that was taken in one of our labs at Google. Okay, good. So these robot arms, what they're going to do is each robot arm has a tray of junk in front of them, and they try to pick up the object. And they either succeed or they fail. And if they succeed, they hold it up and they say, aha, I got it, right? And this camera takes a picture, and so we know that it succeeded that time. If it comes up empty, we know that it failed. And these robots are learning by example to succeed or fail in picking up objects. And they're all learning from each other. So when one of them succeeds, they're all learning about something about how to pick up things in the real world. And that's kind of cool. And turns out that it may be easier to program a robot to learn to delicately pick up a teacup than it is to write a formal set of equations for picking up a teacup. Okay. So we started our deep learning team, the Google Brain team that I work on. We started it in 2011. It didn't work at all for the first year, but then over the next few years, you see a rapid increase in the places that it's used within Google. So this is a graph of all of the places in Google's code that this technology is being used. And it's being used across all of the product areas that we have. And this is part of why people start talking about Google as an AI-first company, because we realize that this is general, and this is important to everything that we could possibly build. So again, this question is, but why now? But why now? If deep learning is so like artificial neural networks of the 80s and 90s, why is this happening now? And again, it's the same story that when data size, when we had little data, and we had little computational power, other approaches were better than neural networks. They were more successful. But when you have more computational power, you're able to move to larger data sets and more complicated artificial neural networks, more complicated and elaborate sets of equations, and then these things start working much, much better than the other techniques. And this leads me to kind of the fourth and final piece of this, which is that what you really need is you need tools and algorithms that are easy to use. And so this is one of the reasons why at Google, my team at Google has helped build something called TensorFlow, which is an open source machine learning platform that you can get at tensorflow.org or at GitHub. And the point of this is to build, to take away all of the basic underlying pieces of software so that you don't have to write it over and over again. You can just build on top of it. And this is the same software library that we use internally to build all of our machine learning systems. So the good news is there are many open source packages for this that are available. It is not a privately held technology. We open sourced TensorFlow in the middle of 2015, and it's gained rapid adoption. And that's partly because this is our second version of a library. There was actually a first version that we started way back in 2011 that was not open sourced, but we only open sourced version 2. I'll skip these. But one of the things that TensorFlow allows you to do is it allows developers to move very quickly because they can work on all different kinds of hardware platforms without having to reinvent the wheel all the time. But one of the things is that, so most of the engineers who work at Google went to school before machine learning was cool. And so we've had to train thousands of engineers to use machine learning for the first time. And so when we built TensorFlow, we also built a lot of educational materials to explain how neural networks work, how machine learning works. So like, even on the outside, you can go to a website called playground.tensorflow.org, and without writing any code at all, you can hit, play in your browser and watch a machine learn. And you can change the building blocks that go into that and watch it learn. And the point is to understand the fundamental concepts about how the individual pieces inside learn to play a part in solving a bigger problem. The problem that you solve here is something very simple, like tell the difference between the blue dots and the orange dots based on where they're localized. But you can see the individual parts working together. You can also explore kind of more complicated systems. So this is a classic problem in machine learning, which is just recognizing handwritten digits. And this is looking inside the neural network and seeing how it's separated out the different digits in its thinking. So this is, I think, kind of the complete picture is that you need computational resources, you need examples to learn from, you need tools and algorithms, and you need creativity and ingenuity. And the thing is that particularly the things on the top, the computational resources and the tools and algorithms, they used to be barriers to entry. It used to be very expensive to get access to appropriate computational resources, and it used to be only a few select labs that had access to the software. And now the software is freely available and open source, and the computational resources are a commodity. You don't need to buy anything. You can just use, you can rent the resources that you need on Google Cloud or Amazon Web web service or Microsoft Azure so that you only use exactly what you need. And so then the question becomes really about the creativity and having examples to learn from in your particular problem. So just to close, I'll say that machine learning I think is already in a whole bunch of products and services, but there are so many more opportunities that I can't even imagine, and that's part of why we're trying to make this technology available globally, because I believe that people all over the world should become craftsmen in these technologies so that they can build what it is that they want. So the final summary points, the things I hope you remember. So the differentiation between artificial intelligence, machine learning, and robotics. So artificial intelligence is machines that appear to be intelligent. Machine learning is machines that move. Machine learning is machines that learn, and robotics is machines that move on their own. I can't believe I got that wrong. Cutting-edge machine learning is actually already in real products. So the best machine learning in the world is in your phone. So that's actually where most of the people that are working in machine learning, that's where the technology ends up. Machine learning isn't magic, but it may be a new technology fundamental, right? I think it's a natural extension of data science, and every place where data science was important, machine learning is going to be important. It's important to understand that currently machines learn best from examples. They don't learn from just a mess of data and gain insights about it. They learn by being fed a huge number of correct examples and imitating those examples. It's not very smart. Why is this happening now? It's mostly because computers are finally fast enough. Making machine learning work in practice requires these 4 elements. The main thing that's in limited supply right now is human creativity and experience with these tools. Of course, we need cheap computation, but it gets cheaper every day. We need data, we need examples to learn from, but there are more examples to learn from every day. We need tools and algorithms, but there are already many open source versions of these tools. TensorFlow is the open source tool that we use at Google, and you guys are free to use as well. And before I take questions, I just want to say thank you from the literally hundreds of people at Google whose work somehow went into these slides. It's not as though I did all this. I didn't do any of this. So thank you for having me, and I look forward to your questions.
Good evening. Thank you so much for your lecture. My question is, what do you think is the biggest challenge the artificial intelligence is facing? We had the Go game. There was machine translation. What do you think is the next biggest challenge for AI? Thank you.
So the question is, what is the next big challenge for AI? And I think that the next big challenge is actually about fluid human interaction. And in order to be able to interact conversationally with a machine, I think a machine is actually going to have to begin to get some grasp of emotional intelligence. And emotional intelligence is something that we really don't have in artificial intelligence systems, and even some of our engineers need help. And I think that this is an example of an area where there is a lot to learn, and I think it's going to be very hard and pose new challenges.
Good evening, my name is Dmitry. Thank you so much for your very interesting lecture. I have several questions. Number one, we saw a linear formula on your slides, Y equals WX plus B. My question is, will there ever be systems, or maybe there are already examples, when the machine is developing the function of non-linear recognition? Maybe it's alien to the human brain, but it's suitable for the machine. And my second question is, when we talk about machine learning, what is stimulating the machine to improve? What boosts the machine to get better?
Yes, these are very important questions. So the example that I used was the linear relationship simply for the purposes of illustration. And in fact, the neural networks are highly nonlinear functions. So they're still a function, but it's a highly nonlinear one. And that's actually part of the reason why we have to use this simple approach of reducing errors, which is sometimes called gradient-based learning, is that we know how to do that even for very nonlinear functions. And so as an engineer, when we put the architecture together, what we're sort of doing is we're constructing the set of nonlinear functions that we're considering, but then the optimization itself is highly nonlinear. There's another potential part of your question is machine learning actually choosing which kinds of nonlinearities to use? And the answer is right now, mostly no. So right now it is mostly a human engineer that decides what the nonlinearities are, and the machine simply has to work with them, but this is some area where we may see some advance. The next part of your question is, what drives the machine learning system to improve? And the answer is simply that we told it to. So this is also something, I didn't go into this part in the talk, but this is something that is expressed in the blue box, in the machine learner part, the learning algorithm, where it's actually written in mathematics what to do in response to an error. And so we actually write that in response to an error, thou shalt change the parameters so that the error gets smaller. And a very simple common mistake is the first time someone writes the code, they forget a minus sign. There's a minus sign in a very annoying part in one particular equation. They forget a minus sign and the machine goes out of its way to make the errors bigger. Obviously it doesn't learn very much. But it does it simply because it was told to. So AlphaGo, for example, it doesn't play the game of Go for love or for beauty or for glory. It plays the game because it was told to predict the next move or to predict the move in the final version. To predict the move that will maximize the probability of winning. It doesn't care about anything else. It doesn't care by how much it wins. A human player would normally care both about the probability of winning and the margin of victory. That's a natural sense of winning that humans have. But this machine is programmed only to maximize the probability by winning, even if it's only by one star.
У нас следующий вопрос. Человек, который по-русски не может его задать.
Hi, I speak Australian, so hopefully you won't need a translator.
Maybe a little.
I'll speak slowly. I'm interested if there's any political obstacles that you foresee in the growth of this area. We know that China's got one of the first major supercomputers. Is that something that Google can partner with? Are there any other challenges that you foresee coming in the near or distant future?
Yeah, so I do think that there are some challenges. I view the biggest challenge is about the democratization of the underlying know-how. So I think that it would be unfortunate and a bad outcome if it would only be a few places in the world where people actually know how to use this kind of technology, and you had just a few hotspots where this kind of innovation was happening. And I think that this is actually quite hard to solve because it builds on so much. It builds on basic science, technology, and engineering education. It depends on the availability of computational resources. But I think that this is a problem that is solvable. I also think that there's kind of a question about how how technologies are used and deployed, I think that right now we're actually in a very good state where researchers, whether they're academic researchers or industrial researchers or government researchers, are publishing their scientific findings. But this is a fragile balance. And I think that it's very important that we maintain this high standard for publishing new big ideas so that we all understand as a global scientific community what is the cutting edge. And I'm concerned about there being a formation of siloed technologies.
I didn't to that.
Hi. I get a question about neural networks. So, I'm here. Yeah. So, neural networks, they are basically used as a replacement for query-based systems. So, how do you go from something that's able to answer queries to something that has consciousness?
Right, so the question is about consciousness and how we get to consciousness. So I'm actually very interested in the study of consciousness, both from a philosophical point of view and from a neuroscientific point of view. What is consciousness what gives rise to consciousness in the brain? This is something that is only beginning to be studied seriously in the scientific community. And so since we don't know what it is yet, it's actually for me very difficult to imagine how it's possible to build it. I think that from a philosophical point of view, maybe it's the case. But right now from a practical level, I feel that we don't know how far we are. We may be, I suspect that we are incredibly far. Because as you see, what is possible today is really very simple. It's really specific inputs, outputs. The machine doesn't know what it's doing, why it's doing it. It has no memory. I think that we are very far.
Спасибо. Собственно говоря, я думаю, что у огромного количества людей, здесь практически у каждого есть аккаунт в Google. И получается, компания Google собирает огромное количество данных о каждом из нас, о нашем поведении, о том, что мы выбираем, как мы живем и так далее. Собственно говоря, вопрос первый. Как вы считаете, кому вообще вот эти вот данные принадлежат? Это, они должны принадлежать компании Google или все-таки это некая наша персональная частная жизнь? И вопрос второй. Давайте заглянем, посмотрим в будущее. И представим, а не сможет ли в будущем на основе технологий искусственного интеллекта, машинного обучения компании управлять общественным мнением и менять потихоньку представление, подталкивать нас к какому-то выбору дальше? Спасибо.
Right, so the first question is about data and personal data. And I believe that data is fundamentally, our own private data is fundamentally our own to control and to understand how it's being used. So for example, I watch movies on Netflix, and I understand that which movies I watch and which movies I like, that is private. I don't want anyone to know how much I like Titanic. It's a big secret. So it's very private what it is that we each watch and what it is that we each like. But we understand that it's okay if the company uses those data to improve recommendations for all users altogether. That's an appropriate use and one that we expect. But if the company were to use the data in a way that violated our expectations, right, where it was instead to send me mailing advertisements at my home for cruises or something because they know I like Titanic, that would be terrible. And I would feel as though my privacy had been violated. And so I believe the answer for Google and for all of these companies companies, is to be clear with users about what it is the data is used for and what it is that it's not used for. It's not the case that when you use a service, you give up all of your rights. It should be an understanding about what the relationship is. And when you move, you should have, if you decide that you no longer like this email service, you no longer like this search engine, it should be made as easy as possible to move from one service to another. So I think it's about trust, and it's about honoring what it is that users genuinely expect. So for example, concrete Google example is that when you use Gmail and you mark things as spam or not spam, you're cleaning up your own inbox, but you are also making spam detectors better for everyone. And Google uses that data to make Gmail better. It's true. But I think that that's an appropriate use. In terms of public opinion, I actually think that what I'm most interested in is public discourse. So I believe that artificial intelligence, machine learning, data privacy, these are actually very important social issues. And it's actually not really appropriate for any one part of a society to choose what the answer is. I think that this needs to be the beginning of a discussion where there's kind of an open scientific understanding about what's possible, an open product understanding, and open conversation also with users, with regulators, so that we as a society make choices together. And different parts of the world also should be free to make different choices. And I think that this is something that in a global world and in a global scientific community is something that is sometimes hard to understand, is that different localities in the world can have different standards for what privacy is. They can have different standards for what they expect data to mean. They can have different choices about where they want to use machine learning or not. Like, so for example, I work on some machine learning for healthcare applications. And that's because, if my mother is going for a cancer biopsy, I want the most accurate answer possible, and I'm okay with using machine learning for that purpose. But someplace else in the world might decide that we don't want machine learning in that kind of application. I think that we should begin that conversation now.
Окей, давайте еще 5 вопросов. Вот сейчас молодой человек там, да, и потом я запомнила еще 2 людей.
Большое спасибо.
Thank you very much for your very illustrative and extremely interesting lecture. My question is very similar to the question asked previously. Still, you might feel it's a strange question, but if this idea came to my mind, I think it has already come to your mind as well. What do you think, by which year will the artificial intelligence replace the US government? At least in part of economy.
There was so much laughter that I
by which year will artificial intelligence replace the US government, at least in economic decision makings?
Oh boy. So I actually think that the kinds of things, if I answer the question seriously, there's a very funny answer that I want to give. But to answer the question in all seriousness, I think that the way that artificial intelligence is really useful is to understand data and to understand trends and patterns. And I actually do think that there are important parts of economics and social policy where machine learning can be used as an additional tool, as an addition to statistics. And I think that there can be some interaction there. But I think the kind of thing where it's an open question is, for example, some people talk about, should we use machine learning in criminal justice sentencing in order to recommend sentences? I think that that is a very difficult decision to make, and it's one that needs to be considered very carefully. I don't think that there's an obvious right answer. Even as a technologist, I feel like that's a very delicate decision to make. And we as humans should always think of the tools that we build as things that are fundamentally there to assist us. They're our tools. They should serve our needs. And I hope that all of our governments serve our needs.
Спасибо за доклад. Вопрос такой, может быть, наивный, может быть, уже ответил на него, но все-таки задам. Есть ли эксперименты по созданию сетей, которые, собственно, могут создавать и настраивать другие сети, да, так двухуровневая история, чтобы, возможно, ускорить какие-то задачи или решать задачи, которые считались невозможными? Или, может быть, на текущем этапе развития технологий это пока не имеет смысла вообще? Спасибо.
So this is a very good question about whether machine learning can be used to make machine learning easier. The answer is definitely maybe. So this is it's actually a very exciting area of research because right now machine learning is actually very difficult. And every time someone who knows machine learning, we're fundamentally very lazy. When we see something that is difficult, we think, oh, how can this be made easier? So there's a lot of research in this area. I would say right now, this doesn't work so good, right? But maybe in 5 years or so, actually machine learning will be made easier by this. It's still very much the case, though, that we're talking about a situation where the real creativity about asking the right question, about framing the problem, about having the scientific insight comes from the human, and then it's just a matter of how easy it is to get the machine to actually work. But I'm very hopeful.
Один тебя на стороне. Да.
Здравствуйте, я здесь. Прямо мне монитор. Я хотел задать вопрос касательно безопасности, искусственный интеллект, машинное обучение. Мы на пороге того, что джин наконец может выйти из бутылки. И как сделать так, чтобы понять, что он вышел и вовремя его остановить? И второе, как сделать так, чтобы этот джин все-таки был в руках хороших парней, а не других? Делать ли что-то в этом направлении?
Yeah, so these are great questions, and I think that this is a very important area, and is part of the reason why I travel and give these talks. Is because I think that this is a time when we have to think carefully about and hard about these issues. So on the question of safety, there's actually been some very good work in the last few years where engineers are actually taking very seriously the question of safety and how we understand safety. Safety in machine learning should be as boring or as exciting as safety in automobiles, right? When we build automobiles, we have certain standards about what we expect machines to do and not do and what is acceptable. And we should have the same approach when we build bridges or airplanes or machine learning systems. We can make safety an engineering objective. And there's actually good hard-nosed research about that that's just happening now. On the question of how we keep the technology in the hands of people who are most interested in good, this I think is a big question, right? Ultimately, these technologies are what we make of them. And it's our choice how we use these technologies. And I think that open discussion about what we think fair use of technology is, what we think appropriate applications are, is something that needs to happen openly in the society. There is a new organization, a new international nonprofit that Google has contributed to, and many other companies have too, as well as non-governmental organizations, called the Partnership on AI to benefit people in society, but just Partnership on AI. is trying to promote awareness and discussion about these issues so that we can kind of work together. Because I also believe that whenever we have new technologies, we have a responsibility to think hard about what we think is appropriate use of those technologies.
Добрый день. Спасибо за лекцию. В настоящий момент я занимаюсь как раз проблемами машинного обучения и пытаюсь их применить к анализу города. И поэтому мой такой вопрос. В принципе, задача классификации, думаю, уже решена. И вот я столкнулся с тем, что свойство нейросетей в том, что она может абсорбировать знания с очень многих людей, с очень многих специалистов, то есть там тысячи, миллионы людей. И поэтому такой вопрос, когда мы можем решать задачу не классификации, но задачу синтеза, когда мы, то есть как с вашей точки зрения мы можем увидеть там новые объекты дизайна, там, новые города, новые какие-то такие вещи, которые возвращены именно системой от многих миллионов людей. Спасибо.
Yeah, so the synthesis question in artificial neural networks and machine learning in general is something that is very hot right now. And in the last 2 years, we've seen a lot of work on a particular technology called generative adversarial networks, or GANs. And GANs are, it's an interesting and very creative idea where what you do is you have one neural network that tries to produce artifacts, generate things. And there's another neural network that's trying to guess whether the artifact is real or fake. And these two neural networks compete and they teach each other. The discriminator gets better at detecting fakes, and the generator gets better at producing fakes. And the fakes are never perfect, but it's actually this technology that has allowed us for the first time to have machine learning systems that actually produce images and produce sounds. And this has been hugely impactful in the research community in the last couple of years, and is really, it's a lot of papers if you search for GANs right now. It's still a very new technology, but I think that you'll see more of that soon. And I think that I'm very excited, for example, to see more of computer-generated imagery, computer-generated sounds. It's not like the real world. It's not natural, but it's a machine fantasy. It's very interesting.
Hello. Thank you, Greg, for your lecture. My question is, you talked about the barriers that existed in computational resources, etc. And there is an opinion that IT giants like Google, Amazon, Facebook, they are sort of monopolies that enable them to create the cutting-edge product. Do you think that these companies have the, how to say, unfair advantage, and how will this problem be solved in the future? And my second question is, where is the fundamental difference between what machine learning technology and classical econometrics, because both of them are targeted at reducing the number of mistakes?
Yeah, so the first question about, is there an advantage that these big companies have in trying to work in these space and developing new products? And I think that there's a lot of competition right now between companies to try to build products that are innovative, and I think that competition is healthy. But I think everyone in the field understands that this is a very early moment, and that actually there will be very important big ideas that come from a small number of people that have the capacity to really change what is possible. And I think that each of these companies just hope that those people will come and work for them. But the basic setting is actually one of disruption, one where innovation really changes things very rapidly. And I think that there's a different world where the software libraries are hard to get at, and the computational resources are all controlled by a few companies that won't give anyone else access to them. In that world, I would actually be much more concerned. I feel like the world that we have right now is one where very small startups have the possibility of really making big changes, and that's the world that I prefer. Your question about econometrics, so it's actually the case that all of these fields end up being interrelated with each other as you study them more deeply. Many of the underlying mathematics are shared. And indeed, I've worked with people who were trained in economics or statistics first as their primary fields. I was first trained in physics, right, where I was used to a different kind of approach to numerical optimization. But the fundamental mathematics are quite common. They're basic linear algebra. They're basic vector calculus. These are things that are taught in many disciplines, sometimes the same ideas with different names, but they come together around these ideas of minimizing